Okay, I've got power, so let's go ahead and get another video in to help you guys out during this rather unusual winter time. So 6.4 is talking about graphing. So we have to graph several exponentials. State of Texas mandates that you know what a couple of them look like. And honestly, most of our rules are going to be pretty much the same. Let's start with our basic parent graph for exponentials. There's going to be y equals 2 to the x power. You should be getting something like this. Now, this does not look very much like a lot of the other graphs that we've done this year. This is a very different looking graph. So a couple things of note. So just like we talked about in 6.3, anything to the 0 power is 1. So 2 to the 0 power gives us a nice even point at 1. 2 to the first gives us 2. 2 to the second gives us 4. 2 to the third gives us 8. So there's some nice little key points along our graph. Now remember, a negative exponent actually flips it. So 2 to the negative 1 is actually a 1/2. 2 to the negative 2 is a quarter, and we see this pattern of it coming down. So it flattens out, and we can go as far as we want over to the left, and it just stays pretty flat. It gets closer and closer and closer to the x-axis. All right, so when we look at this, there are some key characteristics that we can examine. So first of all, domain. Remember, again, domains are left and right. Our domain is going from negative infinity to infinity. It always works, and that's going to be true for all of these exponentials. It works just fine. We don't have any problems with it. Range is a little bit weirder. So on our parent graph here, the graph is going all the way down to 0, but it never actually gets there. So when we actually talk about the range, we're going to be going from 0 to infinity, but the 0 needs to be marked with parentheses. Let's see if I can kind of show what it would look like here. So it's going to be 0 and then going to infinity. Wow, I really cannot spell this morning. Okay, so that would be what our range would be. So domain and range, pretty much the same, just be careful of the domain or the range always having that parentheses because we can't actually get there. Now, next thing, x and y intercepts. Y intercepts are really easy. We're just going to plug in the 0 for x into the equation, and we get it comes out nice and neat, 0, 1. X intercept is often going to be a lot harder for these. So in this parent graph, 2 to the x, we don't have an x intercept. It never actually goes down and touches. So we would label it as not applicable. In the case where the graph does cross it, you don't really have the tools yet to solve for that exact value. So I'll take an approximation. So as an example, if our graph was instead something like, well, that one's actually easy. One of these sometimes get a lot harder to find that exact value. You'll notice that it's rounding it. It's not actually 1.585. It's something a little bit uglier. So when we go through these, as long as you're fairly close as to what the x-intercept is, I'll accept it. Next unit, we'll learn how to actually solve for that exact point and how to calculate it. And I'll still ask for boundaries. So what's the min, what's the max? That's all the same. So let's talk about kind of the shape of the graph itself. So when we start manipulating these, our basic generic form is going to look something like this. I'm going to type it out on this. We'll see how it works. It's not going to actually graph it, but then we can see. So that's our generic parent formula. A, B raised to the x minus h, oops, plus k, not minus. And most of these things still have the same rules. So every single unit, especially starting with unit 2, we've talked about h is a horizontal shift, left or right. It just moves the graph to the right. K is going to be a vertical shift up and down. So for example, if I come up here and I say x minus 2, it's going to shift the graph 2 units to the right. So we've moved it 2 units to the right. If I added 5 at the end, it's going to move the whole graph 5 units up. So those two still work the same. H shifts it left and right, K shifts it up and down. The important thing to note here is that K is also going to tell us the equation of the asymptote. So remember that an asymptote is a line the graph gets closer and closer to, but does not actually touch. Every single one of our homework problems and all these exponential graphs we're going to examine have an asymptote, and it corresponds to the K value. So on this particular graph right here, our asymptote would be y equals 5. That's the value that the graph gets closer and closer to, but does not actually touch. Now the a value, the number out in front, say like negative 0.5, still has all the same things that we've talked about before. So again, positive or negative will tell us if it goes up or if it goes down. Greater than 1 is going to be a vertical stretch, less than 1 is going to be a vertical compression. So all the a value rules are exactly the same as they were in previous units. What's a little bit weirder here is that b value, the number that we're raising to a power. So let's go all the way back to our parent graph and kind of take a look at our basic parent graph again. If I take that b value and I make it bigger, so let's say y equals 5 to the x. Hope if I can type today. So notice what happens. So the red line is our y equals 2 to the x, and it comes up. The green line is going up faster, but it also slams down against the asymptote a lot faster as well. If we magnify this even further, say like y equals 10 to the x, it goes up even faster than the 5, and it comes down even faster. But the asymptote is staying the same. So the first thing that b value does is it affects how fast it goes up. If it's greater than 1, it's going up. If it's less than 1, well, we'll see that in a minute. So let's try a value that's a little bit even less. So rather than 2, let's try like 1.5 to the x. If we did that, notice that this is actually a lot flatter. It goes up much slower. It takes a lot longer to get down to the asymptote. So that's our first change. The b value effectively changes how steep the curve is, how fast it goes up, how fast it goes down to the asymptote. Now there are a couple other weird things about the b value. So if I take that b value and I make it less than 1, so if we make it some kind of fraction like 1/2 and raise it to the x power, equals, it actually flips it. So having a value between 0 and 1, so having a basic fraction in here, will actually reverse the graph's direction. So y equals 2 to the x comes this way. If we flip it to 1/2 to the x, it actually reverses left and right. So that's the next thing. So if the b value is actually, or if the absolute value of the b value is less than 1, then we end up reversing the general curve. We can also reverse the general curve by making the x upstairs negative. So if I take 2 to the negative x, that also reverses the curve, kind of oddly enough. All right, you've done a bunch of graphing at this point. We've graphed every single unit. You know how to do it. The biggest mistakes that I'm seeing people make as we go through the graphing systems or graphing these is 1, messing up the range. 2, not being accurate with the graphs. Use graph paper or be very, very careful with it. I am taking points if your curves are not correct. So actually plot the correct values and then draw the curve for it. Don't just slop it onto the paper. And then oddly enough, I'm going to point this out. So a maximum is the biggest y value that we get. So if I looked at the interval from say 1 to 3 on our 2 to the x curve, if I plugged in a 1, I'd get a value of 2. If I plugged in a 3, I'd get a value of 8. 8 is my maximum. 2 would be the minimum. It doesn't matter what the x values are. I'm only asking for what the actual max and minimum value is, not the coordinate point. So remember that. All right, that is pretty much it. This homework is just a lot of graphs. So be careful, plot them carefully, make sure you're answering everything that is being asked.